Hello all, welcome to KU Padashala, the official YouTube channel of University of Kerala. Myself, Dr. Deepthi from the Department of Chemistry. Today, I am going to talk to you on the topic chiroptical properties, which includes optical rotatory dispersion ORD and circular dichroism CD. Before going to the topic, let me tell you about the nature of light. Light, as we all know, is an electromagnetic wave composed of magnetic field and electric field components. The electric field component actually determines the polarization of this light. Ordinary light is unpolarized, and that is because the electric field component oscillates in all possible directions. And this is the light that we use in UV visible spectroscopy as well. Now, if we pass this light through a polarizing filter, it gets converted to plane polarized light or linearly polarized light. That means the electric field component oscillates only in one particular plane. This light, again when passed through a quarter wave plate, it starts rotating. So it can either rotate clockwise, then it is the right circularly polarized light, or it can rotate anti-clockwise, then it is the left circularly polarized light. So the emerging light is a circularly polarized light. Now, we know that instead of this quarter wave plate, suppose I am keeping an optically active substance there. Depending on the chirality of the substance, the light can either be rotated to the clockwise direction, that means then the compound is dextrorotatory, or the light can be rotated to the anti-clockwise direction, then we say that the compound is levorotatory. And that is how we define the optical activity, which we learned in the first semester MSc classes. Optical activity is the ability of the compound to rotate the plane of polarized light. And specific rotation is given at which is taken in a particular temperature, it is 20 degrees centigrade, and at a particular wavelength is given by the expression alpha by L into C, where alpha denotes the observed rotation, L denotes the length of the polarimeter tube in decimeter, and C denotes the concentration of the solution which you keep inside the polarimeter, and that is in moles per decimeter cube. So we have to note that the specific rotation in a polarimeter is taken at a specific wavelength, and usually the sodium D line of 589 nanometers is used for this polarimetry. Okay. So specific rotation is at a specific wavelength and a specific temperature. Now the question is, what happens if I change this wavelength? So if I change this wavelength, the rotation also changes, and thus we come to the first chiroptical property, that is optical rotatory dispersion. That means change in specific rotation with respect to wavelength. Okay, so having understood what is ORD, now let me tell you what is CD, or circular dichroism. Now suppose I have an optically active compound and I am passing plane polarized light to the circularly polarized light through this optically active medium. Now the two components of this circularly polarized light, that is the RCP and LCP, is absorbed by the optically active compound to different extent. So there is a differential absorption, and the plot of this differential absorption versus the wavelength is what is called as circular dichroism. So now I hope you understand what is the difference between polarimetry, optical rotatory dispersion, and circular dichroism. So all these techniques are together called chiroptical properties. So before going further, let us try to compare what is the difference between UV visible spectroscopy and this circular dichroism or CD. Now both we should understand that is dealing with absorption of light. UV visible spectroscopy uses ordinary light, whereas circular dichroism uses circularly polarized light. So when a molecule absorbs light, what happens? The electron from the ground state goes to the excited state. So that is exactly happening in both the cases, and the difference is that UV visible spectroscopy we are measuring the absorbance, whereas in CD we are measuring the differential absorption of the RCP and LCP. And because of this differential absorption, the light emerging from a CD will be elliptically polarized light, and this ellipticity determines the magnitude of the CD that you obtain. Whereas in case of UV visible spectroscopy, the ordinary light is emerging out from the medium. Some gets absorbed, some gets transmitted, that is all. So, I hope now you understand the difference between UV visible spectroscopy and CD. So, now let me tell you let us try to compare ORD with CD. So, when you compare ORD with CD, CD I told you is a differential absorption, and ORD is whereas ORD is measuring the change in rotation. So, the plot for CD is delta epsilon versus wavelength, whereas the plot for ORD is rotation versus the wavelength. Now, CD is causing elliptical light to emerge. I told you the light emerging out will be elliptical, whereas ORD is causing the rotation of the plane polarized light. Now, if you take the spectra, in the case of spectra, CD spectra will be resembling the UV visible spectra, but it can be either positive or negative, whereas ORD spectra can be a plane spectra or it can be an spectra with peaks and troughs, which we will be seeing soon. Now, CD spectra is actually happening in the vicinity of an absorption band where the chromophore absorbs, whereas ORD we are just measuring it over a range of wavelengths. So, in all we have to understand that both CD and ORD is referring to chiral compounds or non-racemic mixtures, and they are not shown by achiral molecules or racemic mixtures. And these two techniques are very useful to elucidate the configuration of molecules. So, and nowadays the ORD spectrum is totally not used in many places, but the CD spectrometer is used instead, and this is the diagram of a CD spectrometer which I have shown in my slide. And before going further, let me also introduce two terms. One is circular birefringence and another is cotton effect. So, what is circular birefringence? We all know that when light passes through a medium, it undergoes a process called refraction. Refraction is essentially the bending of the light when it passes from one medium to another, and that is because the difference in the speed of light in the two media. So, when an ordinary light bends, there is no further component in that, but when a circularly polarized light is bending, the two components, the right circularly polarized light will bend to a different extent than to the left circularly polarized light in an optically active medium. In normal molecules there is no difference, but in optically active molecules the extent to which RCP bends will be different from the extent to which LCP bends. Okay, and then we say that the medium is circular birefringent and the phenomenon is circular birefringence. Okay, so having understood that, let me tell you what is cotton effect. Cotton effect is just the combination of circular birefringence and circular dichroism. And cotton effect was found by Ami Cotton in 1895. He was a French physicist. The sign of the cotton effect is ultimately going to determine what is the configuration of our compound. So, now let us go into detail about optical rotatory dispersion. So, we have already seen that optical rotatory dispersion means it is the variation of rotation with respect to wavelength. There can be two types of optical rotatory dispersion curves, plain ORD curves or anomalous ORD curve. So, the figure shows you a plain ORD curve. So, plain ORD curve you do not have any peak or trough. You can see that the rotation is plotted against the wavelength. Now, when but we can say that there are two types. The plain ORD curve itself can be either positive or negative. Positive ORD curve means as you decrease the wavelength, the rotation increases, and negative ORD curve means as you decrease the wavelength, the rotation also decreases. But when we get this type of plain ORD curve, it essentially means that your molecule is not absorbing in this wavelength region that you are measuring the rotation. Okay, so that is not of much use. But suppose I have a compound which is optically active. It can be an optically active chromophore, like for example the hexahelicine. It is inherently, the chromophore is chiral, or it can be some functional group which is near to a chiral center, because of which it attains a chirality. That means it is asymmetric because it is near to an asymmetric environment. Example is a carbonyl group. So, carbonyl group adjacent to an asymmetric environment can be taken as an example of a molecule which shows anomalous ORD curve. Anomalous ORD curve is also called cotton effect curve. So, and here we have peak and trough. If the peak is at a higher wavelength than the trough, then we say that it is a positive cotton effect curve, or if the trough is at a higher wavelength than the peak, then we call it as a negative cotton effect curve. The sign of this cotton effect is going to determine the chirality of your chromophore. Now, there can be different types of curves as seen from my slide. You can see there can be single cotton effect curves as well as multiple cotton effect curves, where we have more than one peak and trough. And this particular figure is taken from the book Spectroscopy of Organic Compounds by P.S. Kelsey. So, in this you can see the UV visible spectrometer, UV visible spectrum, as well as the CD spectrum at the right side. So, the peak which is on the top side is the positive cotton effect curve, and on the lower side is the negative cotton effect curve, so negative CD. And below what you see is the plain ORD curve, and on the right side you have the cotton effect curves, that is positive or negative. And for a CD cotton effect, it is very important to know that for a CD cotton effect curve, there is a corresponding ORD curve also, and the wavelength at the crossover point will actually depend, or which will actually the wavelength change at the crossover point will correspond to the maximum wavelength of the CD curve, as is very clear from the figure. So, lambda 0 is the wavelength at the crossover point. So, that is going to correspond to the wavelength maximum lambda max of the CD spectrum. Okay. So, having understood the basics of CD and ORD, now let us go to the real application for elucidation of configuration of compounds using these techniques ORD and CD. So, to elucidate the configuration of compounds, we have two semi-empirical rules, and these include, the first one is the helicity rule. So, helicity rule is for chiral chromophores such as helices and biphenyls. Actually, this is out of context from our present video, so I will not be discussing on that. Instead, I will be discussing on sector rule. Sector rule is for achiral chromophores such as the carbonyl compound. And sector rule can be of two types, Octane rule and axial haloketone rule. So, let us try to understand what is this Octane rule and axial haloketone rule. So, in sector rule, actually what we do is, we will divide the space around the chromophore to different sectors, and each sector will have a different contribution to the cotton effect, and absolute configuration for the molecule is actually assigned based on the sign of this cotton effect. And also we can assign the absolute configuration of homologous and analogous molecules also using this sector rule. So, for example, let me take the example of cyclohexanone. Cyclohexanone, you can imagine that in a three-dimensional space, and you can divide this into 8 sectors or 8 quadrants, as you can see from the figure. So, that is the octant. So, you are dividing the space around the cyclohexanone to 8 different quadrants. And we place the cyclohexanone in such a way that the oxygen atom is facing us, that is, it is in the front sector, whereas all other carbons and its along with its substituents goes at the rear sector. So, in such a situation, we understand that the front sector is not that important to decide the configuration, whereas the rear sector is the one that is important, because all the substituents and carbons are all lying in the rear sector. So now let us come to the statement of Octane rule. So Octane rule states that substituents in the lower left and upper right makes a negative contribution to the cotton effect, whereas substituents in the lower right and upper left makes a positive contribution to the cotton effect. Okay. So you can see from the figure how the cyclohexanon is placed. So in the sector rule, as I told you, the cyclohexanon is actually divided into different sectors using nodal planes. So we have 3 nodal planes, one in the x direction, another in the y direction and another in an z direction, and these planes are actually cutting the cyclohexanon into different sectors. And I already told you that the substituents, and it is very clear from the figure, the substituents and all the carbons are lying in the rare sector. So the rare sector is important to decide the absolute configuration, and it contains all the substituents, and from the Octane rule we can see how the rare sector contribution comes in. The lower left and the upper right makes a negative contribution to the cotton effect, whereas the lower right and upper left makes a positive contribution to the cotton effect. Okay. So along with that, we should also understand that substituents lying in the nodal plane does not make any contribution. Substituents lying in the nodal plane does not make any contribution, and contribution of hydrogen atom is ignored. It is very small, it is ignored. So the overall sign of the n pi star cotton effect is actually determined by the contribution by these various octanes. So positive sector makes a positive contribution, negative sector makes a negative contribution. So what is important is you should be able to identify where your substituent lies. Is it in the positive sector or is it in the negative sector? So accordingly you can assign the cotton effect and you can assign the absolute configuration. So I am talking all this only in the case of carbon substituents. If you have oxygen or nitrogen substituents, things will differ. So we are not discussing on that. Now the substituents which lie in these nodal planes or which are very close to the nodal planes does not make any contribution to the cotton effect. That is another point that we have to note. So if you place, as you can see from the figure, I have shown you the 3 planes there. So the substituent in the fourth one, the fourth carbon, whether it is an equatorial substituent or an axial substituent, both of that is lying in the plane, so therefore does not make a contribution to the cotton effect. Similarly, equatorial substituent in the equatorial position of carbon 2 and carbon 6, okay. So that is also lying very close to the nodal plane, so does not make any contribution to the cotton effect. So in total we can say that the axial substituent at 2 and axial as well as equatorial substituent of 5 makes a positive contribution, as you can see from the green lines there, whereas substituent at 3 and 6 makes a negative contribution, as you can see from the pink line that I have shown there. Okay. So this is the way that we should arrange the cyclohexanon. So that is how we can tackle problems based on CD. So here we see the rare sector. So this is the rare sector contribution. You can see the 5th position positive, 2nd position also positive, the 3rd and 6th position is both making negative contribution to the cotton effect. Okay. So with this, let us try to solve some problems to understand the real application of ORD and CD measurements. So this is one example where the question given is the compound R plus 3-methyl cyclohexanon exhibits a positive cotton effect. Apply the Octane rule and predict the preferred conformation. So then what you do is you have to draw R 3-methyl cyclohexanon, and you have to now draw the chair form, and when you draw the chair form and place it inside the octant. So when you place it inside the octant, you know that as the methyl group is alpha, you have to show it as in an alpha orientation. So if I show this particular orientation, my methyl group is in the 5th quadrant, and 5th quadrant we have already said is making a positive contribution. And from the question we have seen that this compound is exhibiting a positive Cotton effect. So, that means the structure that I have drawn is correct. Alternatively, if I had drawn another conformation as I have shown in the right side of the slide, we have the methyl group pointing down. So, again it is pointing down, so your structure is correct, but it is an axial orientation. So, now when you place this in an octant, this is coming in the third quadrant. Third quadrant is actually should have a negative contribution, but the question says it is having a positive contribution. So, from that we understand that what we have written on the right is a wrong structure. So, we can avoid that structure. Okay. So, I hope you understood what is the application of what we have discussed now. Now, let us try to do another problem, that is the determination of configuration of ketosteroids. So, we are taking a little more bigger molecule, instead of cyclohexanone we are taking decalone. Okay. So, decalone as an example, for example. So, here now we have to, there will be more number of carbons, because you are taking a fused ring system, you have more number of carbons, and so we have to understand that sector with most number of carbons will make major contribution to the Cotton effect. So, this is trans 10-methyl 2-decalone, you can see from the figure, trans 10-methyl 2-decalone. So, this compound, if you really look into the quadrant, you place this inside the quadrant and look in the quadrant, you will understand that the B, you have an A ring and a B ring. The B ring is actually lying in the positive quadrant, and the statement is sector with more number of carbons will make major contribution to the Cotton effect. So, as the B ring is lying in the positive quadrant, this molecule will be showing a positive Cotton effect. So, we can say that this is a plus enantiomer. Whereas, if we draw the other enantiomer, that is instead of trans, if you have the cis 10-methyl 2-decalone compound, this is the cis fusion. Now, we say that the B ring is coming in the negative quadrant. When it comes to the negative quadrant, it will be showing you a negative Cotton effect. So, it is a minus enantiomer. So, like this we can differentiate between the cis and trans form using CD. So, with that let us come to, so I hope you have got an idea about octane rule. So, basically you are placing a cyclohexanone in space and you are dividing the cyclohexanone using nodal planes, and in such a way that you get 8 sectors. Okay. And the cyclohexanone is placed in such a way that the oxygen atom is pointing towards you. So, that is in the front sector, whereas the carbons and other substituent is pointing away from you, that means they are all in the rear sector. So, because this is a chromophore which is inherently not symmetric, inherently achiral, but due to the presence of chirality in adjacent position, this chromophore is chiral. So, therefore, rear sector signs are important, and rear sector is the one which is contributing to the Cotton effect. Now, let us come to the next sector rule, that is axial haloketone rule, which again can be considered as the octane rule. So, before going to axial haloketone rule, let me just explain to you about this type of alpha haloketones. So, here we are telling about alpha haloketones. We know that because of the unfavorable dipole-dipole interaction, the halogen at the always at the second position in a cyclohexanone always prefers to take an axial orientation instead of an equatorial orientation. So, that is something that is already known, and therefore, this is called axial haloketone. And this axial haloketone rule states that the position of the halogen actually determines the sign of the Cotton effect. Okay. So, if you view this axial alpha haloketone through the oxygen, as we have seen in the case of octane rule, if the halogenous atom is seen at the right side, then you have a positive CE, whereas if the hydrogen atom the halogen atom is seen at the left side, then you have a negative CE. Okay. And this effect is also similar in if the substituent is NR2, SR or SO2R instead of halogen. So, we view the ketone along the OC bond in the direction of the ring with the CO group at the head of the chair as usual. If halogen is on the right, then the compound shows a strong positive Cotton effect, and if the halogen is on the left, then the compound shows a strong negative Cotton effect. So, this again is an image taken from the book Spectroscopy of Organic Compounds by P.S. Kelsey. So, here you can see that 2-bromocyclohexanone is given to you. So, when depending on what is the configuration, like for example S, if it is S2-bromocyclohexanone, it shows a positive C. Why it shows a positive C? Because now you can apply your Octane rule, and you can think that the bromine is coming at the second position, and second position makes a positive contribution. So, you have a positive Cotton effect, or you can just take it very simple. You view the cyclohexanone along the oxygen, the bromine you see on the left side, right side bromine means positive C Cotton effect. In the other example, other enantiomer, that is the R2-bromocyclohexanone, you can view it in the octant. When you view it in the octant, you can see that this is the 2, 3, 4, 5, 6, sixth position, and sixth position we know has contributes a negative, comes in the negative sector. So, it shows a negative Cotton effect, or it can be you just view through the oxygen, you can see the bromine on your left side. So, left side means you have a negative Cotton effect. So, axial haloketone rule can be simply ascertained in this manner. Here is another example. So, in this example we are taking ketosteroid again. So, this particular ketosteroid on bromination results in a compound having a negative Cotton effect. So, that is a question. The question is, what is the structure of the bromo compound? So, this ketosteroid I am brominating. When I brominate, I am getting a compound which shows a negative Cotton effect. Where does the bromine come? That is a question. So, applying the axial haloketone rule, we can immediately say that when we look through the oxygen, if it is a negative Cotton effect, the bromine should be on the negative side, I mean on the left side. So, the structure of the compound will be as shown here. Okay. Another example, this particular decalone, it's trans 2-decalone, minus trans 2-decalone, and alpha bromination yields a compound with a positive Cotton effect. Where does the bromine come? That is a question. So, here again we can say that because it is a positive Cotton effect, you view through the oxygen, bromine should come on the right side, then it makes a positive contribution. So, therefore, the answer will be as shown here, and it will be an S configuration, the compound will be S configuration. Here is another example, that is two positions are available for bromination. So, essentially when you have this type of carbonyl group where you have two positions, almost equivalent positions, the bromine can either go one side or the other side, right. That is what we observe when we do the experiment. So, here the question is, when you do alpha substitution and you take the CD of your compound, what you see is a positive CE. So, if you see a positive Cotton effect, then that means the bromine has come to the right side as shown on the top figure. But if you observe the product as having a negative CE, then means the bromine is coming on the left side. So, this is the application of Cotton effect and how the sign of Cotton effect is determining your configuration of the compound. I hope it is clear. So, in summary, to conclude, I will tell you that CD and ORD measurements are useful to assign, to know the chirality of compounds and to assign the absolute configuration. So, here we are using circularly polarized light, and it is because of the differential absorption of the right circularly polarized light and left circularly polarized light that this phenomenon of CD is happening. And depending on the sign of the Cotton effect, we can assign whether the enantiomer is plus or minus. So, that is all I have to say now. So, thank you all.